Hey guys, welcome back to the YouTube channel. So here, the last class discussed a problem. So I hope you guys can able to solve this one. If not, also not a problem. So let me solve it. So I have given a clue. So why I have chosen like this way, not like A, B, C is that here selection line is paired together. So that's why I'm making the pair of those things. So when the selection line is 0, 0, output will be C. So here the C is here, C bar is here. So I'm given C. So if selection line AB which is equal to 0, 1. So this is 0, this is 1, this is 2, right? So if the selection line is 0 and 1, then the output is 1. So 1 means both the things need to be selected here. Okay. So then if the selection line is 1, 0, 1, 0 means then the output is 0. So if the selection line is 1, 0, output is 0. So it means the both is null here. So if selection line is 1, 1, then output is C bar. So C bar is means here 1 and this is 0. Okay. So let's take this case and let's analyze it. So we have to group this together. So this is what the k-map structure for this function. So this structure is mapped to k-map here. So we can group like this way. So this is the best possible grouping that we can do in order to reduce the redundant. So I hope f can be equal to, so let's take this one. So this the common thing is b. So b here and c bar, right? So here the common thing is a bar plus c. So a bar c. So this is the respective Boolean function that we can get from here. So I hope this gives you a good understanding like how you guys can do it the things. So let's continue with another one question so that you guys can understand this in a very good manner. So I'm giving you this time, last time we have given a mux, right? So here let me give you the implicants. So let me give you some implicants like the min term thing I will be giving. So you just try to implement the same thing there. So on the next page I'm giving you the next question. The question is that the f of a comma b comma c which is equal to the summation of min terms which is 0, 1, 5, 7. So let's take random numbers. So now you guys have to implement this in a mux. So please implement a 4:1 mux. Okay, so you please implement a 4:1 mux with the help of these things. So let's take the truth table here. So let us draw a k map first. So from the k map, let's map that to a mux. So let's draw a 3 variable k map. So here I'm going to select C as a selection line. So I'm going to change this accordingly. So anything, it's your input. You can use any kind of thing as a selection line. So here I'm going to use C as a selection line. Okay. So here is C, here AB. So C is 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0. Okay. So let me mark these values. So if we mark it, then here it is 1, then it is 1, here it is 1, because it is 0, 0, 1, 0, 0, 0, 0, 1. Okay. So this will be termed as 0, 1, sorry, 1, 0, 1, 0, 1, 1, right? So this will be termed as 1, 0, 1. So here it will come. So here the 7 will be written as 1, 1, 1. So 1, 1, 1 is here. Okay, please carefully map the values because we have reversed it. So A, B, C. It's not A, B, C. C, A, B. C, B, C, A, B not. So A, B, C. So we have to clearly map it. So from here, let's see how the inputs are getting changed here. So let me parallelly map this with the mux. So as this is a 4 input mux gate, so we need 2 selection lines here. So that's why we have drawn the logic like this way. Okay, so here the A and B are the 2 selection lines we are taking into account. So let's take the selection line which is A and B. Okay, because this is an 4:1 mux, so 4 inputs need to be there and 2 selection line need to be there for that. So okay, so this is 4:1 mux, output is Y. So output is F. Okay. So when selection line is 0, 0, both outputs are 1. So here the output will be equal to 1. When selection line is 0, 1, output is 0. So here output is 0. When selection line is 1, 0, then output is C. When selection is 1, 0, output is C. Selection line is 1, 1, then also output is C. So this is how the implementation of 4:1 mux with the help of the given function. So if you implement this one, the output logic will be summation of m which is equal to 0, 1, 5, 7. Okay, I hope you guys able to understand, right? From mux to function as well as function to mux. Okay, so I hope with the help of this, we can implement any kind of mux as it is possible. So let me give you some bonus tips. So if you have a 4:1 mux with you, what are the possible things that you can do? Is that we can implement any logic because this is an universal gate, right? So we can implement any logic. So we can implement all two variable functions, and some three variable functions. Not all the three variable function cannot be represented, and some three variable functions. If we have 4:1 mux plus one inverter means not gate. Okay, then what we can do is that we can implement all two variables as well as three variables, all two variables and three variable function. So this is one of the very important question, so please make a note of it. So because we have only one thing, so with the help of one mux we can't do all thing. So if we have inverter, then we can do any kind of logic here. Okay, so I hope this is understood. So let's now go into demultiplexer. So demultiplexer is also one of the very important thing. So before going that, let's see how we can implement higher order mux with the help of lower order mux. For an example, if the question is to implement a 4:1 mux using 2:1 mux. So this is also an important logic we have to go over. So if they're asking this, there is a trick to find out. So 4:1, so like so to 2:1. So divide for the required mux with the available mux plus add this result here and again divide. So the result is here 2 and here 1. So summation is equal to 3. So we need 3 mux to 3 2:1 mux to make 1 4:1 mux. So that is what the thing. So how this can be done is that, so let me draw the quick diagram over here. So this is 1 2:1 mux. So here 1:2 mux. So here is 1 2 mux. So here the selection line is S0. So here also selection line is S0. Here the selection line is S1, right? So here two input that can be given, and here also two input that can be given. So here we are mapping that two input here. Okay, so here that is I0, I1, I2, and I3. Okay, so this is why. So this is how we can do with the 4 input mux, 4 input to 1. So this can be done with the help of 3 2:1 mux. So this is how the higher order mux can be built using the lower order mux. So for an example, if they ask to build 8:1 mux using 2:1 mux, then the process is similar to the above thing. So 8 divided by 2, so plus the answer is 4, 4 divided by 2 plus answer is 2, so 2 divided by 1. So it will be equal to 4 plus 2 plus 1, so which is equal to 7. Okay, so this is how we can build higher order mux with the help of lower order muxes. So now let's start with other things. So even the same, even if they ask us to build 8:1 mux using 4:1 mux, then also the same. The division is will be different. So 8 divided by 4 plus the answer is 2. So 2 divided by 2. So means this is 2. So here this minimum requirement is 1. So here we need 3. So okay. So this is how we will be doing. So from here we are completing all our discussion with the mux. So from the next topic that we are going to discuss is the what is mean by demux and decoder. So those are the things that we are going to discuss here. So let me start with the what I mean by demux. So this is demultiplexer. Okay, the vice opposite of the mux is the demultiplexer. So thing is that, so this is also one of the combinational circuit, single input and multiple output. So single input and multiple output. Okay, so if we take this into diagrammatic representation, the exact reverse of that. I hope you guys are able to understand it. So here the input will be 1, selections line will be based upon the thing n. So the selection line will be n, output will be 2 power n, input will be 1. Okay, so this is what 1 is to 2 power n dmux. So let's get into the core. So let's see how 1 is to 2 dmux will be there. So let me write a truth table here. So this is selection line, so output y0, y1. So selection line is 0, 1. If it is 0, then this will be selected, I will be at y1. If it is 1, then I will be at y1. So this is what the thing. So how this can be represented in a mux diagram is that the selection line, yes, this is y0, this is y1, this is input I. So this is 1 is to 2 dmux. So based on the selection line, output will be checked. The exact reverse version of that. Okay, so I hope you guys are able to understand. So here also the same thing. So implementation of higher order mux with the lower order mux is also same thing. So if they ask us to implement 1 is to 8 mux using 1 is to 2 mux, so just to do the same process, 8 divided by 2 plus 4 divided by 2 plus 2 divided by 2. So answer is 7. Okay, so the same thing like previously how that is done. So I hope the multiplexer and multiplexer is fine for you guys. So let us start a new topic, that is decoder. So decoder is a combination circuit which contains many input and many output. Many input and many output. It is used for code conversion. So main purpose is code conversion. Like binary to octal, so those kind of conversion. So for an example, binary to decimal, so those kind of conversion. Okay. Encoder. So encoder is the same opposite of decoder. So it is a combination circuit, so which too has many input and many output. Many input and many output. Okay. So this is also used for code conversion, the same code conversion. But here the opposite. The example is everything to binary. For example, decimal to binary. So this is one of the major application of the encoder and decoder. So let's see how the internal structure is there. So let's take 1 is to 2 decoder. Here there will be no concept of selection line, those steps are. So here that will be directly applied over. So let me draw the structure. So the input will be A, output will be Y0, Y1. There will be another one term that is enable, En. So this is 1 is to 2 dmux. So let me draw the truth table. Here the truth table structure will be quite different because we need to consider En as also one of the variable. So En is A, Y0, Y1. So if En is 0, enable whatever may be the output that is given to A, the output will be 0, 0. So this is don't care. So if enable is 1, then only the decoder will act. So for 0, the y1 will be enabled and y2 will be 0. For 1, this is enable and this. You can clearly see this is a decimal number and this is a binary number. So that is what we are saying, that is used for code conversion purposes. So inverter is same like the 1 is to 2 decoder without any enable line. So inverter can do the job of decoder, but there won't be an enable. So enable concept will not be there. So that is what they are saying. So let us discuss 2 is to 4 decoder. So why we say many input many output is that here you see this will gradually increase. So 2 per 2 the output general logic will be. So that is why we have mentioned like this. So let me directly write a truth table. So here I am not representing the things. So this is enable input column and here ABC or AB input. and here will be y values. So this is enable as it is on 2 input, so A, B. So here it is a 4 values, y0, y1, y2, y3. Okay. So whatever the case, if enable is equal to 0, if it is don't care, then output will be 0, 0, 0, 0. If that is enable, then only our mux will work, decoder will work. So here it see 0, 0, 0, 1, 1, 0, 1, 1. Okay. So if this is the case, if it is 0, the output will be here 0, rest all 0. So if it is 1, then output will be, the y1 will be enabled, rest all 0. So if it is 2, then output at y2 will be enabled, rest all 0. Okay. So this is how the 4:2 decoder, 2:4 decoder will work. So these are all some kind of things that we need to take. Here if you see, there is one relationship between demux and decoder. Here if you see, there S0, S1 are replaced with the input here, A comma B. Here the enable, in the decoder there will be an enable, here that is replaced with an I. So there will be considered as I. So here that is replaced with enable. So here it is 1:4 demux, but here we will call it a 2:4 decoder. So this is the quite difference. Since the internal structure of the 2:4 decoder is same as 1:4 mux, so sometimes 2:4 decoder will also be called as 2:4 as mux. So here you see both the logic are same. So sometimes we call 2:4 decoder also called as 2:4 demux. So this one you can make a note of it. Okay. Now go to next one. So if they ask to implement 3:1, 3:8 decoder using 2:4 decoder, then here also same thing. We have to take this thing. So the requirement thing is the 2 parallels. So 2 divided by 8 plus answer is 2 divided by 4. So this will be 3. So 3 2:4 decoder is needed to implement the things. So I hope this will be fine for us to do with the decoders. So now let's get into the thing, that is what you mean by encoder. So encoder is some pretty different thing that we can get rid of it. So there is another one thing. So we can implement a full adder using a decoder. So let me erase this one. So implement a full adder. So implement a full adder using 3:8 decoder. So this is also one of the important thing that we have to note it. So please make a note of it and try to solve it. So I will be completing this in the next class so that you guys can able to understand the things. So I will teach this in the next class so that you please try this as homework. So please try this as a homework. So next class I will solve it. So I hope this video is informative for you guys. Please like, share and subscribe the channel so that you guys will be notified for all of my videos.